Imagine one day we forget what are square roots. The buildings we construct might topple. Our stock market predictions would go haywire, and our electrical devices might just electrocute us. If that happened, would we be able to rediscover square roots? Let's find out in 3, 2, 1. Let's start by first drawing a square. To do so, we'll need to click the forward command and the face left command. We'll do forward 1 instead and face left 90. Zooming in and repeating these two commands 4 times, we'll get a square. The challenge is, how can we draw a larger square that is twice the area of this original square? Pause the video here to think about it. The first approach that comes to mind is for us to double the length of the sides. However, this actually quadruples the area, which isn't what we want. Let's try 1.5 times the length instead. This area does look about 2 times the original, but just from eyeballing this, we cannot be sure. We could continue this trial and error approach to find out what the length of the new square should be, but it's quite tedious and rather inaccurate. Thankfully, an old friend of mine called Meno found a better way to do this. We will cut the square in half by drawing a line across its diagonals. Make sure to zoom in to ensure our line is touching the corner. Using one of the triangles as reference, we can draw 3 other identical triangles to form the new square. Since the old square consists of 2 of such triangles, and the new square consists of 4, then we have successfully doubled the area of the original square. Let's review what we did here algebraically. We started with a square of side A, and we wanted to draw a new square of side C, with twice its area, to get this equation. In our drawing, A was equals to 1, and so C squared was equals to 2. However, it was hard to determine what the value of C should be, at least at first. Then our friend Meno came around and helped us to figure out how to use the diagonal length of the square to form a new square. From there, we could see that C is really just the diagonal length of this square. If we simplify this drawing even further, then C is just the hypotenuse of this right-angled triangle, which is 1.414. Notice how if we know what the value of C is, we can easily square it to find out what C squared is. But if we were only given C squared, then we have to reverse the operation from above, kinda like the reversed squared of C squared function, and use a trick with the hypotenuse of a triangle to find C. We shall give this reversed square of C squared function a better name. Let's call it the square root of C squared, since we're finding the root element of the square which allows us to draw it, which is the length of its side. So we have found the square root of 2. We can try varying the values of A and see if we can uncover even more square roots. From this previous area formula, we can find the corresponding values of C squared. And by drawing more of these right-angled triangles to find their hypotenuse, we can discover even more values of C. For the triangle of sides A is equals to 2, its hypotenuse is measured to be 2.828, which is the square root of 8. Continue this with 3, 4, 5 and 6 and so on. We start to populate our table. Although this is great, this method does leave some gaps in our square root table. For example, what's the square root of 1? Or the square root of 3, 4, 5, 6, 7, and so on. We need more methods to uncover those missing square roots. Another easy way for us to do so is to use perfect squares. For example, if we have a square of side 1, then its area, C squared, is 1. And thus the square root of 1 is found. If the side of the square is 2, then its area, c squared, is 4, and the square root of 4 is found. The same goes for when the side is equals to 3, for the area equals to 9, we can uncover the square root of 9, and so on and so forth. These perfect squares help us fill up a few more holes in our square root table. Despite having 2 methods to find square roots thus far, there are still many of them missing from our table. We need to explore a third method to find more square roots. Taking a look back at our triangle approach, I wonder, what happens if the sides are of different length instead? Would the resulting area of the square that's created still be 2 times if we start off with a rectangle instead? So we shall try drawing a triangle with sides 2 and 1. As we draw, we'll figure out the length of the hypotenuse, which is 2.236. Using the hypotenuse as one of its sides, we'll then draw a larger square in white. Next, we try to fit the 4 triangles inside of this new square just as before. But as you can see, the new square that's created appears to be larger than just 4 triangles. There seems to be an additional mini square in the middle. What does that mean? Let's take a look at it algebraically again. We drew the white square with the intention to study its area with respect to the rectangle formed. We thought that it might be twice that of the rectangle, but we're wrong. The area is in fact made up of 4 orange triangles and 1 mini square in the middle. If the sides of the new triangle are A, B, and C, then the area of the white square, c squared, is equals to the area of the 4 triangles, half base times height, added to the area of the mini square. According to the drawing, the long side of the triangle is B, the short side is A, and so the side of the mini square is B minus A, making its area B minus A squared. Simplifying the terms, the area of the triangles is 2BA, expanding B minus A squared gives us B squared minus 2BA plus A squared. The 2 common terms 2BA cancels each other out, and we're left with the final equation of c squared equals to b squared plus a squared. With this new triangle of different lengths approach, we're able to uncover even more square roots. In our drawing, when b is equals to 2 and a is equals to 1, we get c squared is equals to 5 from the equation above. Measuring the hypotenuse, we know that c is 2.236. We can try drawing with more values of a and b. But before we do so, I'll introduce some coding commands to make things easier for us. Firstly, notice how we had to figure out what the turning angle is at line 4 in order for us to complete our triangle. This is different for every triangle. Instead, we can simply use the phase 2 command to make the arrowhead face to any point in the xy coordinate space, in this case 0, 0, the origin point, regardless of where it was facing before. Now we have one less variable to worry about. Next, we draw our square just as before. Since we're going to be drawing many more triangles and squares, we should make them into custom commands, so we do not have to keep repeating our code. To do so, we go to the top and type draw, triangle, do. Since the code for the triangle ends at line 7, we go to line 7 and type END. Do the same for the square. Now, the custom commands triangle and square are defined. You'll notice that nothing's drawn yet. That's because we have yet to call the commands themselves, which we'll do at the bottom. Toggling the triangle on the left to hide the code, we can see the high-level overview of what's happening. With our triangle and square commands, we can add variables to vary the lengths of the shapes. We create the variable b, a, and c for triangle at the top, substitute in the code chunk in the middle, then input the numeric values of these variables when calling the command itself at the bottom. We can do the same and introduce a variable c for the sides of the square. Since both the square and the triangle share the same variable c, we could further combine these two commands into just one command called Meno Diagram. That way, we only have to input the variables b, a, and c once for the diagram to change. Now, we're all ready to continue our drawing. We have to draw b equals to 3 and a equals to 1 next. This means c squared should be 10. By measuring the hypotenuse of this triangle, we get c is equals to 3.162. Keeping b the same and changing a to 2 instead gives us c squared equals to 13. Once again, using the hypotenuse, we get c is equals to 3.606. Continue this and we start filling up even more gaps in our square root table. Unfortunately, despite having found 3 methods to find square roots, there are still significant gaps in our table. Perhaps we should try working backwards instead. Say we want to find the missing square root of 3. We'll let c squared be equals to 3 to get this equation here. So c is just the square root of 3, which is once again the hypotenuse of our triangle. We just need to find the lengths of sides of a and b to draw our triangle. Instead of juggling 2 variables at once, why not we make one of them a constant? We'll make a equals to 1 since a squared is just 1, making things easier for ourselves. That sets the height of the triangle. We're left with 2 equals to b squared, which means b is equals to square root of 2, representing the base of the triangle. Since we know what's the value of square root 2 from our previous exploration, we can draw this triangle to find the missing square root of 3. And yes, we have successfully found a 4th way to uncover these unknown square roots. Let's refine and generalize this case to all possible square roots. To do so, we'll give c a simpler name. We'll call it n. Remember that we made a equals to 1 so that a squared is also 1? Rearranging the equation, we get b squared equals to n minus 1. And finally, b would be the square root of n minus 1. Updating the triangle, if a is equals to 1, then b is equals to the square root of n minus 1. Then we draw this triangle to find its hypotenuse, which represents square root of n. Let's draw this out and see for ourselves. Looking back at just the code for the triangle, we can edit the name of the variables in terms of n. Since the height of the triangle A will always be 1, we don't need the variable a anymore. The variable b changes to square root n minus 1, and the variable c changes to square root n. If we coded this right, then we can draw the triangle for when n is equals to 2. After that, using square root 2 as the base, we can draw the triangle to find the missing square root 3, which is 1.732. Notice we've used 1.414 twice. Once at line 11 as the hypotenuse of the first triangle, and a second time at line 14 as the base of the next triangle. Since the values of these two lines are the same, why don't we combine them and make it one line instead? That will reduce some visual clutter. This way, this line represents square root 2 and this line represents square root 3. If we continue doing this with higher and higher values of n, we will finally fill this holy square root table with all values of n, so that the future generations no longer need to find square roots. They can just look up this table. To access this table in the code, we simply need to type sqrt and input the values of n as well as n minus 1. So we no longer need 2 variables, just 1, which is n. From here, we use recursion to draw all the possible square root triangles. And voila! We've created the beautiful spiral of Theodorus, with every line extending from the origin representing a square root value of n. As we stare at its beautiful lines radiating outwards, we're left with more intriguing questions than before. Do the square root rays from the spiral ever overlap each other? What about the square root of decimal numbers? It's a never-ending, irrational journey of discovery. We hope you've been coding alongside us as we make these discoveries together. Comment below the questions and ideas you've stumbled into along the way. And if you liked this video, do subscribe and let us know what concepts you would like to rediscover on this platform. Till next time, fellow paperlanders. Peace.